Okay, hello everybody. Again, thank you for being here. My talk is a bit of a story about a serverless video transcoder that I built using Lambda, step functions, EFS, S3, and DynamoDB. Now, I have given a talk about a week ago at the Serverless Community Day where I told this story, but this is a new talk. It is all new content and it's a little bit deeper than the previous one I gave, simply because I have more time now. So I hope you stick around, listen to my story, and ask me questions. I have prepared 10% new jokes, so hopefully they will work. First, let me reintroduce myself. My name is Peter Sbarski, and I happen to be one of the co-organizers of this wonderful community day. My day job is VP of Education and Research at A Cloud Guru, and I also happen to be an AWS serverless hero. Some time ago, I wrote a book called Serverless Architectures on AWS. So if you're bored, check it out. So last year, I think it was October or September, Nikki Stone and I were planning a talk for Serverless Conf, which is a big serverless conference. And we were trying to figure out a really interesting topic to talk about. One idea that came to mind was around solving genuinely big problems with a pure serverless approach. If you have a task that takes more than 15 minutes to solve, how would you do it? So from this came a discussion on idea to build a serverless video transcoder to transcode large video files. So our proof of concept would take a file, a video file, and then transcode it to another format or bitrate or resolution. Only Lambda would be used as a compute option. No containers, no EC2, nothing like that allowed, just Lambda. When we write software, we often think about serial computation. That's what we're all familiar with. We're used to it. So one execution executes after another. So if you think about converting a video file, you run it through FFmpeg, and then it converts kind of like one segment after another, after another, after another, after another, after another, until you get a new file, right? And now, wow, we've transcoded, our 1080p to 720p file. Awesome. It's a paradigm we're familiar with. Obviously, under the hood, there is some parallelization that happens with multiple threads, but that's pretty much how it works. But it's not going to work with Lambda. How would a serverless transcoder work? We knew that the only true way to process a large task of this nature would be to break it up into smaller tasks, process these smaller tasks independently, which could be done with Lambda, and then combine them together to get a result. As you have already guessed, we took our inspiration from MapReduce. So what are the general steps you would need to go through if you wanted to build a transcoder? So first you have the original file, then you split it up using Lambda, then you transcode each smaller portion in Lambda, and hopefully you do this in parallel to make it really nice and fast. Then you begin to merge together transcoded segments. And finally, at the end, when you have merged all the transcoded segments, you have a new file with that different bitrate or different encoding. Pretty cool. And there are a lot of use cases that can benefit from this type of parallelization. Many use cases like serving web traffic to multiple users or rendering computer graphics, genetic algorithms, computer simulations, Monte Carlo analysis, facial recognition, neural networks, parallel computation, optimization, searching large data sets, so on and so forth. There's just a lot of different use cases. Now, one more point before I describe our algorithm. There is a paper and presentation from the Usenix Symposium on Networked Systems, Design and Implementation that showcased a video encoding system running on Lambda. Now, what these researchers from Stanford, UC, San Diego, and MIT did was very innovative and different. And they did this a few years ago, and I didn't even know about it until somebody showed it to me. So they designed a framework to run general purpose parallel computations on a commercial cloud function service like Lambda. So this system starts up thousands of threads in seconds and manages inter-thread communication. So these different threads can talk to one another. Another thing that they did was that they implemented a brand new video encoder to take advantage of that fine-grained parallelism provided to them by Lambda. In our algorithm, as you will see in our system, we use off-the-shelf software like FFmpeg, FFprobe to analyze our videos, split them up, transcode. It's good, but it's not as fast as building your own specific encoder that is optimized for parallelism. So this awesome experimental system that they built ended up producing fantastic results. So as I mentioned to you, they came up with two major contributions: a framework that could run 5,000-way parallel jobs on Lambda, and that encoder with massively fine-grained parallelism. They compared the system that they built called Xcamera to VPX encoder, which is a library you can run on Linux to encode video files, and to YouTube. And you can see the results right now. A 14.8 minute 4K video took only 2.6 minutes to encode using Xcamera versus 37 minutes when they did it via YouTube versus 149 minutes when they ran VPX encoder on a C3 8x large instance with the local SSD RAID array. And by the way, they were writing everything to RAM. That's amazing. And then when they ran VPX encoder as a single-threaded operation, it took 453 minutes. Incredible. And I will take a sip of tea while you absorb these incredible results. So that's great. But I'm not as smart as these amazing researchers from MIT, UC San Diego, and Stanford. So how does my implementation work? Well, look, let's first of all look at the services that I ended up using. And I'm going to exclude things like IAM and just focus on the important ones. So we have S3, we have EFS, we have Lambda, we have step functions, and DynamoDB. I should note that I have built another version of this serverless encoder, which only uses S3 and doesn't use EFS, and one that uses SNS instead of step functions, so you are not locked into using any of those services. To me, EFS especially is a bit of a question mark, but I will talk more about it later. Importantly, I'm also using FFmpeg, which is running as a Lambda layer to perform the actual cutting and merging of video files. Obviously, it gets executed by Lambda, works nicely. So let's talk about the algorithm at a high level. So here's the high-level architecture. And the purpose, as I said before, is to transcode from one bitrate to another, or from one format encoding to another encoding. So let's maybe think about this as we are transcoding from 4K to a 720p video. So first you upload your video file to an S3 bucket. Awesome. That kicks off a Lambda function that analyzes the file and figures out how to split it up based on keyframes. Good. It then invokes step functions and passes that useful metadata to it. One of the actions that step functions does is run the split audio function. So the split audio function takes the video and extracts and saves the audio file to a folder in EFS. It also updates the database, DynamoDB, so that the system knows what's happening and the state it's in. And we are splitting the audio here because we found that it makes the overall process a little bit faster, but you absolutely don't have to do it. You can leave the audio and the video intact as well. One of the parameters we passed to step functions was an array which specifies all segments that the original video file needs to be split into. So for example, we may have 512 items in that array that specify the start time and the end time of each segment. Using the map type in step functions, we create a fan-out effect. So step functions creates 512 Lambda functions, or more or less depending on the actual number of segments you want to create. These run in parallel and create tiny video files that are then saved in EFS. And it also updates, they also update DynamoDB. Now the split operation doesn't just do the split, it also converts the file from one bitrate to another, if that's what we're trying to do. I probably could have used a different function for it, but it was convenient to do everything in one, especially because we were using FFmpeg. The next step begins our merging process. We have our converted segments, and now we need to merge them together. An interesting property of our system is that neighboring segments can be merged as soon as they are ready. We actually create a binary tree of segments to allow for more efficient merging. But that's a story for another time, I think, and possibly a chapter for, a second edition of an upcoming book, maybe. After all segments have been merged together into a new file, step functions invokes the final function that takes the new video file together and the audio and combines those two. The result, our new transcoded file, is uploaded to an S3 bucket, and the operation completes. Now, please indulge me for just a little while longer. I want to spend 2 more slides just to talking about step functions. With the step functions map type, you can create really interesting fan-in and fan-out operations. And this is great for things like MapReduce. So here's a diagram that actually shows the logic that takes place between the split and the merge video functions. You can see that first we do the split, then the system has a choice whether to begin merging. If it chooses to do so, it continues to kind of loop until all merging operations are completed. Then the merge audio task is called and the workflow continues onto something else. Now, what is cool about this is that the logic here is partly expressed by how step functions are defined. Step functions decide what happens next based on that definition and based on the return output from each Lambda function. So it is very, very useful. Here is a screenshot that I took from step functions. This is what it actually looks like. In fact, you can step through all parallel executions in step functions. And it is maybe not the most intuitive interface that you have ever seen, but it really helps with the debugging and understanding of what's happening in the system. I have the entire system, as I have mentioned to you, implemented using SNS. And when something with SNS fails, well, it's not often fun, let me just say that. You have to go for CloudWatch, you have to look at X-Ray. This actually makes things a little bit easier sometimes because you can go and look through different execution paths and even compare the inputs, the outputs, and what's happening in your system. Step functions makes it a bit simpler. So check it out. I wrote a blog post about how I used EFS with my serverless transcoder. And so I quickly wanted to run through it because I had a lot of questions. I'm going to show screenshots and quickly describe how to get EFS working with Lambda, but if you want more detail, please refer to my blog. It has a step-by-step tutorial. One thing I should note, you should obviously be using infrastructure as code. Use CloudFormation, use SAM or serverless framework when it begins to support this. Should be soon, I hope. I'm showing you how to do it manually so that you know what happens, but please use infrastructure as code yourself. EFS requires a VPC to function, unfortunately, but that's okay. So the first step is to create a VPC. Then you open the EFS console and click Create File System. From the VPC dropdown, select your VPC, keep the default settings, and just click Next. Pretty simple. On this next screen, keep the throughput mode on bursting. You need to watch the burst credit balance metric in CloudWatch. You could choose provisioned mode, but provisioned throughput, but it can be very expensive, and trust me, I know. So be very careful if you choose provisioned. Then you'll need to configure an access point and set user permissions. Pretty easy to do too, but again, check out my blog post on read.acloud.guru for more information on what you need to do. Finally, you review configuration and click Create File System. It may take a little bit of time, but it's not outrageous either. Next, you open your Lambda function in the Lambda console and scroll down to the File System card, and then click Add File System. And by the way, it goes without saying that your Lambda function has to be deployed to the same VPC as where you have your EFS system. Select the EFS file system, select the available access point, and then type in a local mount path like /mount/data, for example. You can choose your own. Having done that, click Save. Now you should see the EFS file system information as well as some cool things like the access point ARN. That's it. You now have access to the entire EFS file system as a local disk drive through your code. It's mounted on the path that you specified before. It's easy. You can now write code to access that directory, create new files, delete files. The code that you see on the slide is from the serverless transcoder. So one snippet creates a bunch of directories. Another snippet actually writes a segment or that short video file to EFS. Oh yes, one trick if you don't deal with VPCs very often. So your Lambda functions are now in a VPC, which means that you must correctly configure security groups and net gateways if you want your functions to talk to other AWS services or to external endpoints. But, if you don't have to mess around with security groups or net gateways, it's better not to. You can use VPC endpoints instead. So if you need to use services like S3 or DynamoDB or step functions, then VPC endpoints can make life really easy. You configure them in an instant and you don't have to worry about changing function code or configuration. Everything continues to work as before. Obviously, you have to pay for, VPC endpoints, but, you got to pay for everything, right? So let's talk about some of the lessons that I learned by building the serverless transcoder. So first of all, the longer the duration of the video, the better the outcome. And by better, I mean it is really faster. So if you have a longer video, you can subdivide it into many segments, transcode them parallel, and have a result. You actually see the advantages of a serverless transcoder in a more apparent way when the file is longer, because it runs so much quicker than if you just ran it on a regular computer, which would do that kind of serial conversion. Step functions plus map, so the map type, is better than using SNS and fanout for this task, I believe. Again, just the observability, the ability to look at different execution paths and understand how things fit together are awesome. It doesn't mean that you couldn't use SNS though, it still works. EFS offers new opportunities for serverless applications. Absolutely, you can now run more things, more applications, more services in Lambda with EFS than you could before, but be careful, and I'll talk about what you need to be careful of in a moment. I think we still need better abstractions, so if I want to, build awesome MapReduce applications, it's still a little bit too hard. I think there are ways, there are things that AWS could implement to make our lives a little bit easier. We need more specialized libraries as well. If we're using Lambda, like those researchers have created, it would be good to see more specialized libraries we could use for Lambda. DynamoDB is great for keeping state, for kind of helping us keep records. We use expiring TTL, so our records get deleted a few hours after, and that keeps the database nice and clean. EFS made the implementation of the serverless transcoder simpler and more succinct, that's for sure. Made things a lot easier than just using S3. But the price and performance of EFS on Lambda is still something that I need to look at. I have a feeling that S3 is still going to be cheaper, but I need to check it out and do some calculations. Obviously, you need to run EFS in a VPC. It would be great if you didn't need to, but such is the case. And as Ben Keogh said to me, if you replace S3 with EFS, you lose some of the kind of nice cloud-native features of S3, like the ability to view and change contents in the console or the notification system or access logs. So you kind of have to weigh up the pros and cons. That's it. This is the end of my talk. Check out my blog post at read.acloud.guru. I go into more depth and provide more information. I would love to hear from you. I would love to connect with you. So please follow me on Twitter or connect with me on LinkedIn. With that, thank you so much for joining our community day. I hope you enjoy both days, and I will see you next time.